Okay, thanks, Charlie. So hopefully you can all hear me. I'm going to talk today about sort of the outgrowth of work from my postdoc years with Charlie not too long ago. And so the papers that are sort of the foundation for what I'm going to be presenting today appear here. And about this phenomenon of which we call branching patterns or branching flows, which arise when you try to transport stuff as quickly or efficiently as possible. And actually this here is kind of in a nutshell the takeaway message of the talk, which is that if you can imagine that instead of allowing physical forces like gravity or buoyancy to move fluid around, if it's say hot on the bottom and cold at the top, if instead you allowed yourself to reach into the fluid and move it as you, so it's sort of an optimal design problem or an optimal control problem, well then these are supposedly the streamlines of a fluid flow, a steady in time fluid flow that is built to try to maximize the rate at which hot particles go from the bottom to the top. And it's sort of complex, multi-scale, and so I want to kind of tell you about how these things arise. But actually, I'm going to focus the talk mostly in work that is, again, an outgrowth from the postdoc, but still in prep. You can read all about this picture in these articles, but it's a little more universal. Actually, it's much more universal than those. And so I want to talk about now a general setting in which involves trying to maximize thermal transport. Okay, so here are two problems to keep in mind, to fix in your mind for the rest of the talk. And again, I have sort of a general family of problems in mind for which these are examples. So the one on the left is sort of the problem that looks almost like Rayleigh-Benard convection, but now there's no momentum equation. So the velocity field depends on time and space, and you're allowed to choose it as you please. You solve a passive scalar advection equation with diffusion. And of course, you can't control the diffusion. It happens at its own rate. You can control the advection. You want to choose the velocity field so that the rate at which particles transfer from the bottom to the top is as quick as possible in some average sense, let's say long time average sense. And here's the problem, which will be familiar to some in the audience. By the way, sort of here are some references for where these particular problems come from, but we'll get into more details of the setup in a moment. Okay, so here's a related problem. Let's say you want to optimally cool an internally heated disk. So now, instead of having just pure advection diffusion, I have advection diffusion and a source term which is spreading, which is inject heat uniformly throughout the disk. And now what I want to do is, well, the temperature is set to be 0 at the boundary, and what I want to do is I want to move the fluid around somehow inside. You can control the way in which the fluid moves around to try to make the average temperature, let's say, as low as possible. So try to transport the heat out to the boundary as quick as possible. So you sense that these two problems are related to each other, and indeed they're sort of two problems that arise in a general class of problems which take the sort of following form. I give you a measure. I prescribe a fairly canonical measure of transport or cooling efficiency, which in the problems I'm talking about today are going to be the mean square gradient of the temperature field. And there's a good reason to consider that in these two problems I'll say in just a moment. And angle bracket for me in this talk is always going to mean a sort of long time space average. So average in infinite time horizon and average in space. And I want to either maximize or minimize the mean square gradient of the temperature field, which is a proxy for the rate of transfer of heat, and I want to maximize it to try to drive the heat from the bottom to the top as quickly as possible, or I want to maybe minimize it, because in this problem, you notice very quickly that if you multiply the equation by the temperature field and integrate by parts, then using the boundary conditions, this contribution from these terms will go away on average in time space, and you'll find a balance law between the mean square gradient of the temperature, average time space, and the average temperature field. So I could have told you to minimize the average temperature, and that's exactly the same thing in this setup on the right as minimizing the mean square gradients for the temperature field. Great. And over here, if I wanted to say maximize the advective contribution to the temperature, to the thermal transport from bottom to top, so that's like the long time space average of the k hat component of u multiplied by t, well, then a similar integration by parts argument will tell you that this is again equal to the long time average of that quantity you want to maximize in this kind of problem that we've seen in previous talks today. Okay, so in either case, I'm going to try to optimize this. And now I need to spend a little bit of time fixing the class of velocities, because if I allow you to move the fluid as quickly as you want, then of course you can drive this down to zero by taking a sequence of ever increasing intensity velocity fields, or you can drive this up to plus infinity. So I need to put some kind of constraint on the velocity fields, otherwise the problem's not well posed. And so I'm going to use the following entropy constraint. There are lots of other constraints that you can put on the problem as well. Here I'm gonna always think about having no slip boundary conditions, okay, to simplify my life. You can also use other kinds of boundary conditions, but behind everything I say today is no slip boundary conditions. And then I'm going to enforce this entropy constraint, which says that, well, Peclet just stands for a measure of the intensity of the fluid flow. And so I decide to measure the intensity of the fluid flow by taking, again, the mean square gradient of the velocity field. So that's this is the mean square rate of strain. And then I set that equal to the Peclet number. And so now I'm trying to optimize the rate of transport or the rate of cooling subject to a constraint on the intensity of the fluid flow. And I want to know, how does the answer depend on that constraint, on Peclet? Okay, good. So why do we set up the entropy constraint? So this is a little divergent from the main goal of the talk, which is to solve those optimization problems. But anyways, why would I think about in using the entropy constraint? Well, because actually you need to achieve, if you're trying to design these fluid flows or realize them in practice, then here's the equation you should be solving. You should be optimizing over the force field F, and it should depend on time and space in some well-chosen way. And so what's a natural constraint on the force field is the amount of power that you spend to move the fluid around. If you put a bunch of fans in the domain to try to move the fluid, then the power that they expend is F dot U, and that is of course going to balance on long time space average with the energy dissipation rate. Nu is the the coefficient of viscosity. Okay, and so there is a balance between, on average, there's a balance between the power used to sustain the flow by some fan assembly that you're optimally designing and the mean square rate of entropy. And so that's why I can just constrain, instead of constraining F, I can just constrain the mean square rate of entropy, and that essentially does the same thing. Now, notice that I'm never talking about realizability questions, okay? So I'm never worried, and of course one needs to be worried about this to realize these designs. I'm never worried about whether or not a given supposedly optimal F generates a stable scenario where somehow the fluid flow converges to what I think it's supposed to be going to in order to optimally transport heat. That's a different and more difficult question than what I'm going to talk about today. And so let me just get straight back to that problem. I've taken away the momentum equation, and I'm just optimizing over all velocity fields U with specified entropy, mean squared entropy. Okay, so these are basically the answers. So, and I'll say up to caveats. So for those of you who are in the know, I need to make a little bit of a correction to this, which I'll put on the slide right now. So we know that in either of these problems, the optimizers for a given entropy constraint, so I'm trying to maximize rate of thermal transport or minimize the mean temperature, so cool the disk as quickly as possible. We know the answers scale, the maximum rate of transport scales in either as Peclet to the 2/3 or an inverse power, the same 2/3 power, but inverse. Actually, we know this up to a logarithmic correction. And so that means that we know that on the one hand, there's an ansatz-free upper bound or an ansatz-free lower bound that says that which velocity field that you choose that satisfy these constraints, you can't beat this scaling. And on the other hand, we can, and this is sort of the main contribution of the talk, one of the main contributions of the talk, we can tell you how to construct a velocity field that saturates those bounds up to a logarithmic correction. Okay, so that's kind of the main takeaway message. And now I want to get into a little more of the details in the case of the heated disk, since that's sort of, I think, new to most people in the audience as far as branching is concerned. But before we get to the complicated flows that appeared on the first slide, which were the branch transport flows, let's step back and look a little bit at the energy constrained transport problem, because that one is supposedly easier. Okay, so let me just sort of tell you what's known and in fact what's not known. You'd like to call this a warm-up, but what's known and what's not known about this problem. So this was a problem studied by Charlie, and maybe Jean-Luc is in the audience, and co-authors. And they said, okay, remember in this problem, this is a proxy for the average temperature. So we're going to try to cool the disk as quickly as possible, minimize the average temperature, or minimize the mean square gradient of the temperature, and subject to it an energy constraint. So I don't constrain the entropy anymore, but rather the kinetic energy of the fluid flow. And that's something I can, in non-dimensional terms, also call the intensity. Now, instead of using no slip boundary conditions, I used no penetration boundary conditions. R hat is the outwards pointing unit normal to the boundary, R hat because it's a disk. And same boundary conditions, T equals for the thermal temperature field. And so what do you think the answer is? Well, they were able to construct by writing down the Euler-Lagrange equations of this problem, which does involve some kind of Lagrange multiplier for the energy constraint. They were able to construct for each given Peclet number a sort of convection roll-like fluid flow. So you can think of this as convection rolls, but adapted to the radially symmetric domain. And there's a stationary zone in the center. There's sort of the bulk behavior is convection roll-like, and then there's a little boundary layer that emerges at the edge where the fluid flow has to turn around. And what they're able to show is that the measure of efficiency of these flows is no larger than, we're trying to minimize it, is at least as good as 1 over Peclet, okay? And so you'd like to say, well, maybe that's the answer, right? So if I think that if I want to try, remember we're trying to cool the disk. So if I want to try to drive the temperature as low as possible, I should set up some kind of flow structure that gets the fluid out to the boundary as quickly as possible. And then maybe why not just convection rolls? That's the simplest thing that you could do. Well, it's not known whether or not this is optimal in any sense. It solves the Euler-Lagrange equations in an asymptotic sense, but it's not known whether or not this state that was constructed in this article is actually representative of the true optimizers in this problem. So that's a nice open problem for those in the audience. Okay, here's what we know about entropy constrained transport in this setting. And actually, these we should think, so as I showed in the setup, there's a general class of problems for which these kinds of results are known. But anyways, let's focus on cooling a disk. So the measure of efficiency of cooling my disk, which in this case is mean square gradient of temperature, scales as 1 over Peclet to the 2/3. Now Peclet is the mean square entropy, or the mean entropy, I guess root mean entropy, and it scales as 1 over Peclet to the 2/3 up to here's that log correction, and so there's a lower bound which says you can't beat that. There's an upper bound which says we kind of know what to do. So I wanted to spend the rest of the talk telling you how we know that this is true and how we came up with this upper bound, since I think that's maybe the most interesting part. Okay, well, not that the lower bound isn't interesting, but I think it's close. The lower bound is closer to things that have already been discussed in these series of sessions, like background method bounds. So the task at hand is to estimate for any given velocity field the mean square gradient of temperature. And one thing that you can do is you can use a sort of test function method. This is not the background method. It's different. You can use test functions. I like to call them eta and xi to prove upper and lower bounds on the mean square gradient of temperature. That holds so long as your test function satisfies suitable boundary conditions. And you can smell, if you know background method, you can smell that this is sort of related to the background method in some way, because if I wanted to now prove an a priori lower bound, I'm trying to minimize the mean square gradient temperature. So if I want now to prove an a priori lower bound, I should maximize over my choice of xi, right? And so how do we get, just a couple words about why this is not the background method and how these bounds come about. So I'm trying to now prove these bounds before I start to use them to solve the optimal transport problem. Okay, so here's how these bounds come about. So the first thing you do is you take this PDE and you write down the formal adjoint of it. And so now you have a system of PDEs. And by the way, why would you want to do that? Well, because if I just step back for a second, if I wanted to calculate the mean square gradient of temperature by some variational principle, then maybe I'm thinking of finding a variational principle, finding a Lagrangian whose Euler-Lagrange equations are the advection diffusion equation. Well, actually, that's not possible to do. If there doesn't exist a Lagrangian that depends on the fields in play, the temperature field and its gradients, in a pointwise fashion that generates this PDE. And the reason for why that is not difficult to understand, because the operator is of mixed type. This is a symmetric operator. This is an anti-symmetric operator. Remember, U is divergence-free. And so try as you might, you'll find that there's no pointwise defined Lagrangian for which this is the Euler-Lagrange equations. Notice, if you change, this depends very much on the character of U being divergence-free. If you let U be curl-free so that it's generated as the gradient of a potential, then it's an exercise in Evans PDE to write down a Lagrangian for that. Okay, good. So we symmetrize. And now that we've symmetrized, we can add and subtract and divide by 2. And once we add and subtract, now we come up with this other system of PDEs, which are equivalent to the original one and its formal adjoint. And what's nice about this is that there's a way to diagonalize. And if you solve the let's say you solve the eta one, you invert the Laplacian, then you have eta as a function, as a non-local dependence on xi. You plug it in, and now you have a PDE that depends on xi alone. So you can decouple this by this sort of solving one and plugging it into the other. And when you do that, you'll notice that the system you write down ends up being symmetric. All the operators are symmetric. So you can hope to write down a sort of Euler-Lagrange type principle for it, albeit involving non-local operators. So here's a little bit about how that looks. So the nice thing about this symmetrization is that it has an orthogonality built into it, so that in a space-time average sense, the gradient of eta and the gradient of xi are L2 orthogonal to each other, again, in a space-time average sense, which allows you to calculate the quantity we wanted to optimize in terms of sums of squares of these quantities, eta and xi. The cross term goes away. And so if I then plug one of the PDEs in for xi, let's say I plug in for xi, then I get what I got from inverting the Laplacian on this equation, I guess. And this variational principle just asserts that if you don't solve the equations but use any choice of test function eta, you get an upper bound. Okay, so then if you minimize over eta, turns out that these are the Euler-Lagrange equations that come out for that. That's where that arises. And similarly for xi. So that was just a few words about how those come about. Now let's try to use that to solve the problem. Okay, so let's prove an a priori lower bound. I mentioned in a couple words a moment ago that this is kind of like the background method, so maybe there's not much to be learned from doing this, but on the other hand, it's just a different way of thinking of things. Let's try. So plug in the xi field. Well, what test function should I plug in? It's probably a good idea to choose xi to have a boundary layer built into it. I'm not going to bore you with the details, but indeed, if you choose a xi function which sort of which is equal to a constant inside most of the disk and then goes to 0 in a rapid boundary layer, you can then estimate all of these quantities in terms of the mean square gradient of U and applying Poincare inequalities where appropriate. And then at the end of the day, you'll be able to prove this lower bound. Okay. That's very reminiscent of the background method, so I don't want to go into very much the details of that because it's the upper bounds, the constructions of the nearly optimal fields, which are maybe the most interesting things. We want to know if these bounds are sharp and in what sense. So is it sharp and in what sense? Okay, so now let's go back to the other one. Okay, so I want to minimize the mean square gradient of temperature. So an upper bound on it is a good thing because now I'm going to minimize that. Okay, so I want to, and also I'm allowed to choose the velocity field to be whatever I want, and I expect it to be quite complicated. So my life becomes easier if I choose it to not depend on time, although that's an open question. So I'm going to choose the velocity field to not depend on time, and then when I do that, I'm faced with the following problem. looks like this. So you can boil it all down to a problem that looks like this. And so what I've done is I've taken my optimal design problem, minimized my measure of efficiency of transport, subject to a constraint. Here I'm sort of relaxing that constraint by introducing something which is equal to 1, essentially. Okay, so I took this constraint and then I rewrote it here as the number 1 disguised. And so then you can check just by algebra that, and by applying that bound on transport, which is sharp in the case of steady flows, that the original problem, which was to cool as quickly as possible, is the same thing as solving this kind of variational problem, which has a non-convex lower order term which prefers patterns and has a regularizing higher order term which somehow knows about, well, which certainly knows about the Peclet number. And as Peclet goes to infinity, this term gets washed out and you're sort of driven to respect the behavior of this lowest order term. But it's really the balance between these that's going to set up the actual chosen pattern. And the claim would be that, well, depending on, now that you've realized that the problem is like this, you should reach back into what you know about problems that look like this and ask, do they remind me of something that I know how to solve? And the answer is they remind me of many other problems that exhibit multi-scale behavior and branched phenomenon, and which are not having anything to do with fluid dynamics, but instead come from problems for which there is a free energy, essentially. So problems from elasticity and micromagnetics. So here I'm just showing a few tantalizing pictures to motivate for you where the idea of branching came from through the functional analysis. If you write down, so this, let's just talk about this one. This is an elastic solid, a bulk elastic solid viewed from the top, which is making a blister. So there's a thin film, there's a thin elastic film. Maybe you can even see the rough outline of the film. There's a thin elastic film which is bonded, but by a weak bonding agent so that it can debond in some place if it's energetically favorable. And so then it does. So it pops up and the block is sort of compressed from all sides. And so this blister pops up away from the block where it debonds, and you see this multi-scale pattern, and the delamination profile is going to 0 at the boundary because that's the edge of where the deglued, debonded versus bonded front is, right? And so that's sort of, now how would you determine the shape of that pattern? You would write down the internal elastic energy associated with this kind of deformation and try to minimize amongst all possible deformations. Well, lo and behold, the elastic energy looks almost identical to this. There are certainly differences, but anyways, if you want to chew on that connection more, I invite you to look at the last 2 sections of the Communications Pure Applied Math paper with Charlie, in which we chew on the connection between this fluid dynamics problem in principle and problems from elasticity and micromagnetics that have a very much similar functional form. And so that all is to say that branching is a good idea. We should try to do something that's multi-scale. At lowest order, I want to be satisfying u dot grad eta. Eta is like a proxy for the temperature field. I want to be satisfying u dot grad eta is exactly equal to 1. But there are many ways to do that. And so here's a way to do it where you see I'm inviting you to imagine a field which branches, which has multi-scale behavior, and the length scale of branching depends on the radial coordinate in this way. So you sort of take this picture from the first slide and you wrap it around the disk, and that's the kind of ansatz that we have in mind. And now we're going to plug that into this functional. We have a version of this for u, we have a version of this for eta, and we're going to optimize. Probably the only thing that, lots needs to be said about that analysis, and I'm not going to go into the details for lack of time. But one thing that is high level and should be said is, how do you choose the way to do a branch? How do you go from a stage where you have a certain amount of convection rolls to a stage where you have double the amount of rolls, right? So you sort of need to do so in a way that respects the format of this functional. And so one thing to notice is that the flux of the eta field by u through any slice is specified as a function of r. That will give you a way in which to design the branching fields. Okay, so that's nice.
Ian, 1 minute.
There's 1 minute left. So I'm going to this slide, which says that if you follow this line of reasoning, it all boils down to a 1D variational problem where you can determine L as a function of R. L is counting the number of rolls. Okay, fine. And at the end of the day, that proves what I wanted. So let's get to the conclusions. So And these general sort of entropy constrained optimal design problems having to do with maximizing measures of efficiency of thermal transport, the answers that we're finding up to logarithms turn out to be multi-scale branching type constructions. There are things that we don't know, and I want to sort of briefly review them because I think there's lots of interesting questions that remain. Firstly, the one thing we do know is that the analysis is much more general than the two examples I've shown. In fact, similar results can be shown if you have a general domain with maybe a squiggly edge, or you have a general domain here with squiggly tops and bottoms. But what about the log? Well, there's this really nice result that came out, this computational result that came out in 2018, which found in 3 dimensions. Everything I've been showing here is 2D, but you can try a version in 3D. So they do it numerically, and they find a numerical result in 3 dimensions that shows that somehow the log shouldn't be there, and that indeed a branching like tree-like structure does exhibit this Pickley to the 2/3 scaling, which if you undo this in terms of Rayleigh and Nussel, formally this predicts an ultimate scaling type behavior. But mind you, we have not enforced the momentum equation. Other questions? Does time dependence play a role? And what about that pesky bound for energy constrained cooling? I think I'm out of time, so I'm going to stop there.